There's a bar here which is connected to the ground via a revolute joint at this location, and it is suspended by the spring at this point. The spring is initially unstretched and the system is at rest. So this is the unstretched length of the spring, that means. And it is connected to this bar at this point. And if this is a uniform bar and it is described as that, the mass center of this bar will be located at, if this is 1.2 meters, 0.6 meters away from the ground. Okay, so this is 0.6 meters. And then the spring constant is given to us, and we are asked to find the velocity of point A as this bar reaches the ground. So it falls in that direction, and it does a pixaxis rotation. And then as it strikes the horizontal surface, we are asked to find the velocity of A just before it strikes, obviously. What we have to consider here is what's going to change in terms of the energy levels of this bar from the initial condition and final condition. The path taken is not of our concern, because at the moment I don't really see any non-conservative force acting on the system. The forces acting on the system are conservative forces. There's the spring force and there is the gravitational force due to the gravitational acceleration in the downward direction. So in terms of the potential energy, what's going to change is this mass center will move from 0.6 meters to 0 meters. Therefore, there will be a change in the potential energy due to the gravitation. Okay, so there will be delta Vg. And that will be the mass of 30 kilograms times the gravitational acceleration. 30 kilograms times the gravitational acceleration times the total distance in the vertical direction that is dropped. So it's a negative distance, negative 0.6 meters. It will have a drop. That's the delta Vg. That's going to appear in our equation. The energy is conserved, so I can say in this equation is delta E, the change in the total energy, is equal to 0. Initially it's at rest, so when we are saying delta T, actually we are asking to find the kinetic energy in its final condition, TF. We are trying to find out TF, and TF could be calculated as 1 over 2 I, if I say this point is O, by the way, IO omega squared. Or you could as well find it out as if I say that this is G point, this is the mass center, 1 over 2 Ig omega squared plus 1 over 2 m Vg squared, and this Vg here is in fact calculated as omega r. Okay, this is omega r squared. Whichever way you want to use it, either you calculate the mass moment of inertia of this link, and then if we consider that this is a slender ring, so Ig in that case would be found as 1 over 12 m L squared, and L here is 1.2, by the way. And you can make use of this information, or you can calculate IO to be equal to this Ig information plus M, and the R here is 0.6, 0.6 squared. That's another way that we can formulate the kinetic energy. Now, in terms of elastic energy, the potential energy due to the elastic materials, the unstretched length is 0.3, and we need to find out the final extension, so from this point to that point. And you can make use of your trigonometry knowledge. This is 0.9 meters, and this total length here from this location can be calculated as 0.3 plus 0.6. This is 0.9 as well. Am I doing something wrong? No, this is not the mass center. Sorry about that. Let me just erase this part. Okay, so this is the point of connection. The point of connection is 0.9 meters away from the rotation axis. So this is 0.9 meters here. And then from this reference point to this location is denoted as 0.3 meters. The total stretch is 1.2 meters here. Initial length is 0.3, so the stretch here happens to be calculated by this total length, which is let's call it x2. X2, or maybe I should call it something else. So x2 is already used. So I need to calculate this total length minus 0.3 will be the extended amount for the spring. So this is the calculation here, 1.2 squared plus 0.9 squared. We'll get this length here, minus the initial length, which is 0.3. The total extension is 1.2. In the initial case, it's extended by 0. That's 1 is equal to 0. So we can calculate the potential energy change due to the elasticity by using this 1.2, which happens to be 108 joules. The potential energy change due to the gravitation is a negative value, as we have discussed here, which is calculated by using this drop of the mass center. It's dropping by 0.6 meters. And the kinetic energy can be calculated by the use of the mass moment of inertia calculated about this point O. And the mass moment of inertia will be calculated as 1 over 12 ml squared plus m. Actually, this is uniform rod, so I can write out L over 2, by the way, L over 2 squared, times omega squared, and then velocity of A, after we find out this omega, is actually going to be calculated as a fixed axis rotation from this point, and the total distance is 1.2. So 1.2 times omega will be the velocity of 8 point, and this is calculated right over here in terms of numerical values.